In this today's lecture, numerical is an I section has the following dimensions: width 300 mm by 10 mm, flange 150 mm by 20 mm. The maximum shear stress developed in the beam is 14.8 MPa. Find the shear force to which the beam is subjected. So, in this numerical, problem statement is to find shear force, not shear stress. Here, see term shear force. We have to find shear force, yes. And in numerical, they have given us shear stress 14.8 MPa. For solving this numerical, same methodology we use. First to find position of neutral axis, second find moment of inertia, and third, by using this shear stress formula, we find the shear force. Data: maximum shear stress denoted as tau max, and this maximum shear stress is 14.8 MPa. And problem statement is to find shear force, yes. First step is to find position of neutral axis. Here, this is I section, and see, this I section is symmetrical about x-axis axis. See, this red line is x-axis axis. Above this x-axis axis and below x-axis axis, both sections are symmetric. This and this both are symmetric. And let us consider this vertical axis as y-y axis. Right side and left side of this y-y axis both are symmetrical. So to finding neutral axis for this section is easy for us, because we don't use this formula y bar is equal to a1 y1 plus a2 y2 plus a3 y3 upon a1 plus a2 plus a3. This neutral axis we get directly. This total distance is 20 plus 300 plus 20. 340. This total distance is 340 mm, and divided by 2 is 170 mm. Somewhere here, x6 170 mm. So total height 340 divided by 2, 170 mm is position of neutral axis. Section is symmetrical about x-axis axis and y-y axis, so moment of inertia calculation also easy for us. In this numerical, we don't use parallel axis theorem for calculation of moment of inertia. See, moment of inertia denoted as I is equal to, first calculate moment of inertia for this full rectangle, this red line, full rectangle, and about neutral axis, x-axis axis. This red line full rectangle moment of inertia is 150 multiplied by 340 cube divided by 12. This 150, this full distance is 340 and divide 340 cube divided by 12. So here 150 multiplied by 340 cube divided by 12. So we calculate this red rectangle moment of inertia, and our section is I section. So subtract this moment of inertia, this two rectangles moment of inertia, from this big red color rectangle. This yellow color rectangles are this 150 minus 10 minus this is 10. 150 minus 10 is 140 mm, and 140 divided by 2, this distance is 70 and this distance is 70. That means 70 multiplied by 300 cube divided by 12. Is 300 minus, and these rectangles are 2, that's why here 2. Sorry. Minus 2 into 70 multiplied by 300 cube divided by 12. So calculate this. 150 multiplied by 340 cube divided by 12 is 491.30 into 10 raised to 6 minus 2 into 70 into 300 cube divided by 12 is 315 into 10 raised to 6. So moment of inertia for that I section is 491.30 minus 315, 176.3 into 10 raised to 6 mm raised to 4. This is moment of inertia for that I section, and this is position of neutral axis for that I section. Now we have to find shear force and in numerical they have given us tau maximum, shear stress at maximum, that means shear stress at neutral axis. So for finding shear force, use this formula. Shear stress is equal to shear force multiplied by area multiplied by centroidal distance divided by width into moment of inertia. And in numerical we have maximum shear stress, and maximum shear stress is at neutral axis. That's why I write here tau neutral axis is equal to SAY upon BY. And our main objective of this numerical is to finding this S. So finding this S is equal to tau neutral axis multiplied by width multiplied by moment of inertia divided by A into Y. So shear force is equal to tau neutral axis is this 40.8 MPa. 18.8 MPa. Multiply by B. B is width. At neutral axis is somewhere here, and so at neutral axis width is this 10 mm. Is B is 10. And I moment of inertia is 176.3 into 10 raised to 6. And divided by AY. So here, for finding this AY, above this neutral axis, find AY. So first, consider this rectangle area. This rectangle is, height of this rectangle is 150 mm and width is 10 mm. So area for that red color rectangle is 150 multiplied by 10. And from this x neutral axis, centroidal distance is 150 divided by 2. So see, A1 y1 plus A2 y2. Let us consider this as so here 2. So A2 area is 150 multiplied by 10 here plus A2 area is 150 multiplied by 10, and this y2 distance is 150 divided by 2. This A1 is area for that flange portion. Area for that flange portion is for that much area 150 multiplied by 20. And this y1 is neutral axis for that flange portion from original x axis. That means this much distance. So this distance is up to here 20 plus 300 plus 10, 330. From bottom up to this distance is 330 mm, and 330 minus 170 mm. 170 is this. This 330 minus 170 is this distance. 160, okay. So calculate this. 150 multiplied by 20 multiplied by 160 plus 150 multiplied by 10 multiplied by 150 divided by 2 is 75 is 5,92,500 is this AY. and consider this shear force equation as 1. So equation 1 becomes this equation 1 is S is equal to, put this Ay value in equation 1, we get this shear force. So our Ay is 5,92,500. So S is equal to 14.8 multiplied by 10 multiplied by 176.3 into 10 raised to 6 divided by 5,92,500. So 14.8 multiplied by 10 multiplied by 176.3 multiplied by 10 raised to 6 divided by 592 500 to 44 into 10 raised to 3 Newton. Why Newton? Because this 14.8 is in Newton per mm square. This moment of inertia is also in mm raised to 4. This Ay A is in mm. This Y is also in mm. So mm square get cancelled. This S value is in Newton and mm. That's why here S, our S output come in Newton. Yes, unit of shear force is Newton or kilonewton. 44 into 10 raised to 3 Newton, and S is equal to 44 kilonewton. So we calculate shear force is as 44 kilonewton for shear stress of 14.8 MPa, and this cross section shear force comes 44 kilonewton. With the help of only maximum shear stress and this I section dimensions, we calculate this shear force as 44 kilonewton. Thank you very much.